Hey guys, Mr. Harrison here from school, coming at you with the slideshow video for heat and thermal energy. So let's get right into it. First question would be, what is heat? And heat is simply thermal energy that's being transferred. And thermal energy, referred to in the heat definition, is the total energy of all the particles in a material or object. Total energy of all the particles. So it's the concept of the total of all of them together. And again, heat is simply thermal energy that's being transferred. So obviously, like one of the greatest discoveries in the history of mankind is the discovery of fire. And since we've discovered fire, we've created a wide variety of devices that help to utilize the heat of fire or other things for our benefit. One thing that we need to talk about in terms of heat and heat transfer is temperature. And most of you know like what it means to check your temperature. You know that it's in usually degrees Fahrenheit in the customary units that we use, but in the metric system we use the Celsius scale. We're also going to talk a little bit about the Kelvin scale, but that's not technically an SI metric unit. But temperature, when we refer to that, we're talking about the average speed of particle motion in a substance. So that is definitely a kinetic energy. It's all about the motion of the particles, because the warmer something gets, typically, the more motion the particles have. Like the more movement, the more the atoms and particles are moving. And there's two kind of no-duh statements up there. The first is when the motion of particles increases, so does temperature. Kind of just makes sense. And the second is the inverse. When the motion of particles decreases, so does temperature. So motion and temperature are directly related. When motion goes up, temperature goes up. When motion goes down, temperature goes down. And then also when temperature goes up, motion goes up. And when temperature goes down, motion goes down. So I wanted to talk for just a minute about the difference, or similarities and differences between temperature and thermal energy. Remember that the temperature is the average, keyword, average kinetic energy of the particles in something. And thermal energy is the total kinetic energy of all the particles in a material. So I want you to answer in your head or write it down somewhere this question. What's the difference there? I'll read the definitions again. Temperature is the measure of the average kinetic energy of the particles in something. Thermal energy is the total kinetic energy of all the particles in a material. So the question is, what's the difference? Take a second and read those again if you're not quite understanding the difference. Now, to illustrate the difference between temperature and thermal energy, I want you to think about an iceberg, and then right next to that iceberg is a boiling pot of tea or water to make tea. So a tea kettle that's boiling hot and an iceberg right next to it. Question. This should be a little more obvious. Which one of those two, the iceberg and the boiling pot of tea, the boiling tea kettle, which one has a higher temperature? And again, this is a little more obvious, but I would think you would know that the boiling tea kettle has a higher temperature. Second question. Between the iceberg and the boiling tea kettle, which one has more thermal energy? Between the iceberg and the tea kettle, which one has more thermal energy? Okay, now follow up. Did you have the same answer for both of those questions? And I know this is kind of rhetorical. I just want you to participate in a way by answering those questions, at least in your head. Okay? Last point, everything has thermal energy, even ice. How do you think this is possible? All right. I'm going to leave you hanging there just for a second. We'll come back to this. So to measure temperature, we use a tool called a thermometer. And that's either mechanical or possibly electrical digital device used for measuring temperature. And the earliest thermometer was invented by a guy named Galileo. And each temperature is going to be according to a scale. It might be Fahrenheit, it might be Celsius, it might be Kelvin. Obviously, as we said before, The only scale we use in the metric system is Celsius, and that's because it's based on water. We'll talk about that in a minute. But it's going to have equidistant measurements, which means they're equally spread apart. And they're marked to use for measurement. And then you'll see how high usually a liquid goes within that cylinder with the notches for measurement. So the first thing we got to know is the Celsius scale. As I said, it's based on water, and it's the most commonly used in the world. The unit for measuring temperature is called a degree, and the Celsius scale itself is based on the boiling and freezing points of water, because water boils at 100 degrees Celsius and freezes or melts at 0. So 0 and 100 are very nice round numbers, which is why we use them. Then we've got the boiling point, which is the temperature at which anything that has this word point is going to be the temperature at which, and the boiling point is the temperature at which water boils, or at which water, as a liquid form of water, turns into the gas form. That is 100 degrees Celsius at sea level. Then you've got the freezing point of water. Again, that's the temperature at which water freezes, or liquid water turns into solid water, and that is 0 degrees at sea level. This altitude can affect that just slightly, but it's going to be really close to 0 and 100, even if it's not at sea level. Then we got another scale we need to know about, and that scale is based on a term called absolute zero. The scale is called Kelvin scale. It's another way of measuring temperature, and it's based on that absolute zero idea. And absolute zero is pretty much exactly what you would think about. When you think about what absolute zero might mean, you're probably right. It's the coldest possible temperature, absolute zero temperature. Remember that temperature is the average kinetic energy, which means motion. So at absolute zero, there is no particle motion. Since temperature is the kinetic energy on average in a substance, absolute 0 Kelvin is 0 movement. There is no kinetic energy. And the equivalent in Celsius to 0 Kelvin would be minus 273 degrees Celsius, negative 273 degrees Celsius. That's really, really low temperature. And since absolute zero is 0 Kelvin, there is no negative kelvins because you can't have less than 0 motion. And absolute zero is the temperature where all the molecular movement stops. Next thing we got to talk about in terms of temperature is expansion and contraction. If you picture like a balloon, if you have an inflated balloon and you're letting a little air out of it, it's contracting. It's getting smaller. It's decreasing in volume or size. The flip side is if you blow more air into the balloon, you're expanding the balloon, or that's expansion, and that is an increase in volume or size of the balloon. And an interesting thing we've figured out over the years is that temperature changes tend to cause things to expand and contract. Things that are heated usually expand and get bigger. Things that are cooled usually contract and get smaller. I remember one time I woke up for school and my dad had his finger underneath the cold water. I lived in Minnesota, so it was cold water in the sink. And I was like, "Are you washing your hands? What are you doing, Dad?" And he's like, "No." He's like, "I slept on my body weight was on my arm last night, and my hand swelled up a little bit. I can't get my wedding ring off." He was trying to take a shower, get his ring off for some reason. And I was like, "That really worked?" He's like, "Yeah." And sure enough, after like a couple minutes of letting his hand be under cold water, the tissue in his hand contracted, got smaller, and he was able to get the ring off. It really does work. It's also why our roads crack, unfortunately, in the winter, but that has to do with the phase change of liquid water to solid, which we will probably come back to a little later. And this phenomenon where heated things expand and cooled things contract is usually more drastic in gases than a little less drastic in liquid, and solids expand and contract the lowest amount based on temperature. So when we talked about heat, that is thermal energy that's transferred, right? So there are 3 main ways to transfer thermal energy: radiation, conduction, and convection. And we'll talk about those 3 right now. Transferring energy is always going to go from an energy source to another object. An energy source is an object or material that can transfer energy to other objects. So the source of the energy is always the one that the energy is going away from to go to something else. And then radiant transfer or radiation is one of the ways that heat energy can be transferred. This is like the magic one. It doesn't even require them to be in contact. It just goes through thin air in the form of electromagnetic waves, which, as we talked about in our previous unit on forms of energy, electromagnetic waves and radiation is the way that radiation or radiant energy is transferred. And the radiant energy itself is it's kind of like circular reasoning a little bit, but radiation is a transfer of radiant energy, and radiant energy is transferred by radiation. It's kind of an obvious statement, but it's all about electromagnetic waves. All forms of radiant energy have this in common. A, they behave like waves. So if you think about like waves in the water, they behave like that. And they also can be absorbed and reflected by objects. So when objects are in their way, they either absorb them or reflect them. The second way to transfer heat is called conduction. And think about it in terms of like electricity. It's the same kind of idea. Thermal conduction is the process of transferring thermal energy through direct contact. The particles are in direct contact. So it's like if I have like a hot spoon and a cold spoon and I put them together and they're touching, the cooler spoon will warm up and the warmer spoon will get a little colder because that's conduction. It's transferring heat through direct contact between particles, or sometimes they say particle collisions, but they're actually touching. Then you got the last one called convection. And convection is the movement of heat through fluids. Many of you don't know, I didn't know this originally, I had to learn it. Fluids are not just liquids. Fluids are technically liquids and gases. Gases and liquids both behave the same way. The only difference is gases do all of the things liquids do, but faster. So gases and liquids are both types of fluids, and convection is the movement of heat through fluids. So that means it's either through liquids or through gases. And the picture before, I think it might be on here again, but the picture from before, this pot, this is convection. And the reason you know is because it's a circular motion of temperature transfer or of heat transfer. That's convection. Warmer fluids, as a general rule, will rise, and colder fluids sink. That's both true for air and for liquids. And this is due to the density. Remember how we said that things expand when they get warmer and contract when they get colder? Well, this applies to liquids and gases as well. And most of you understand the idea that hot air or hot water rises and cold air or cold water sinks. But just think about if you've ever slept in a bunk bed. In the summer, you definitely do not want the top bunk because it's hotter closer to the ceiling since warmer air rises. Likewise, if you've been like swimming in a lake, it's usually going to be colder by your feet than it is by the surface of the water because cold water sinks. And that's because cold water is more dense. So it's in a way, it's heavier, and so it sinks. And then warmer water is less dense, so it's lighter and it rises. And we've covered this before, but this is just a review. If you're constantly adding heat to a substance, take water, for example. You got solid water, which is called ice. If you're constantly adding heat, even though you're constantly adding that heat, when that substance is going through a phase change, the temperature does not change. That's why we have these two flat lines in red here, because this is solid turning into liquid called melting. The temperature stays the same until all of the ice is melted. Likewise, when it is going through vaporization or evaporation or boiling, all of the liquid water stays at the same temperature until it's all turned into a gas, until that phase change is done. So even though the heat remains the same, the temperature doesn't change during a phase change, and that's really important. And the heat that we're adding to it there is called latent heat. And the last thing, I want to revisit our question about temperature and thermal energy, the iceberg and the boiling tea kettle. The one with the higher temperature is going to be the boiling tea kettle. That seems obvious. Which one has more thermal energy? And did you have the same answer for both? Your instinct, if it's like mine, might tell you, oh, obviously if the boiling tea has a higher temperature, then it has more thermal energy. If I would have guessed that, I would actually be wrong. the iceberg actually has more thermal energy, even though the boiling tea has a higher temperature. And that might completely blow your mind, and that's okay. The reason for this is, remember we said that everything has thermal energy, even ice? Well, the iceberg has some thermal energy per square cubic centimeter or whatever. So does the boiling tea. But the iceberg is way more massive than the little pot of tea. So even though the tea has a much higher temperature, since there's so many more water molecules in the iceberg, the solid iceberg actually has more total thermal energy. Because remember, thermal energy is the total kinetic energy. Temperature is the average per particle. But the average per particle is way higher in the tea. But since there's way more particles, the total thermal energy is actually greater in the iceberg than in the boiling pot of tea. I know that kind of probably blows your mind a little bit, but it's the truth. So go ahead and answer the questions attached to this and move on.